Okay, what kinds of questions do you have about today's materials, Kyle? Can I go over protection? Sure.
But then if you did include water, the answer was marked wrong. The correct answer was what it would be.
Oh, and that the online quiz?
Yeah.
I'll go back and take a look at that. Because I may have to go back and give everybody credit if it's, or there may be multiple answers. So that's what I'll be doing the next couple days, is getting everything caught up. What else from today's?
Can you go over the by-air villager contribution?
Sure. Lisa?
Could you go over when you were doing making the protection part? Is it like I guess we're gonna go over it anyways, but like just like the whole mechanism, like
Of the protection?
yeah.
You mean like the mechanism I asked you to do for today?
Yeah.
So protection. So when we get to functional groups, well, when we get to molecules that have more than one functional group in them, the problem that we're going to have is that if I try and do something to one functional group, I have to make sure that I'm not changing or having that functional group then react with the second functional group that's in the molecule. So the one I did at the end of class was a reduction of a carbonyl versus the reduction of an alkene. Here's another one. Here's another example. So I'm in the lab and I said, I'm starting with this alkyl bromide, and what I'd like to do is I'd like to add a carboxylic acid group at the end of the chain. And so what we could imagine is we could say, well, if I'm going to add that COOH group, I'm going to first need to add what to the bromide? I'm going to have to add Mg, magnesium, which is going to turn it into the Grignard. So that's going to turn it into the minus, and then the MgBr plus is the counter ion. Okay. And then what do I need to add to that Grignard to convert it to a carboxylic acid? CO2. So in the second step, I'm going to add CO2. Now, here's the problem with this molecule right here. Grignards react with aldehydes and ketones, or they would deprotonate things. So the problem is, if I turn this part of the molecule into a Grignard, what's it going to do? It could attack itself. So in other words, the minus charge, the carbonyl, could attack that carbonyl like that. And that would form a how many membered ring? So we'd have carbon, 1 ring, 2, 3, 4. Probably that's not going to happen because 4-membered rings are tough to make. 5 or 6, piece of cake. 7, now you're starting to get more difficult. But what we lose track of when we write reactions on paper is, I'm not just reacting one molecule, right? There's like billions of these molecules in the solution. So more than likely what would happen is that Grignard, once it was made, would react with another carbonyl So instead of doing an intramolecular reaction, it would do an intermolecular reaction where it would come down here, bless you, and add to that ketone. Because it's not just one molecule that I'm working with. And whichever one happens, my Grignard's going to be gone before I ever add the CO2.
I'm confused, but that instead of adding it, that intra.
So intramolecular would be if
First way you
would be this way. So
why
that
are
would
we
be,
doing intra?
well, the intra would make a four-membered ring. And making a four-membered ring is kind of tight in terms of sterics. If there was another carbon there, it very well might form a five-membered ring. Five-membered rings and six-membered rings are really easy to make. But it doesn't really matter whether it happens by intra or whether it happens by an intermolecular between two molecules. I lost my Grignard.
Where would you get the Grignard if you didn't use the intra? So, like, I know you're making one, but, like, it seems like you're making a chain and then just using the...
What I'm doing is I'm just adding the magnesium here and making this.
Right.
Once I make this, it's going to look around for carbonyls to react with.
Okay.
And it either finds itself or it finds another one.
Okay, and the other one is the one that's on the other side? Or?
Well, all I did was I took another one of these molecules and brought it down. So these are two of the same molecules.
Yeah, that's why I was confused. I just felt like we got it nowhere. But...
Well, that's what I was saying. When we do reactions on paper, we just think that I have only one molecule. And I've got probably at least, even if I had a tenth of a mole, how many thousands and millions of molecules is that? So there's always another molecule around. So the Grignard, when I make it's going to instantaneously react with the carbonyl of itself or with another molecule. And so when I go to add the CO2, I don't have the Grignard that I wanted. So this is where I would protect. So this is where I'd say, you know what, I need to protect that carbonyl. So I would take the ketone, and before I added magnesium to it, I would say, let's go ahead and react this with ethylene glycol in the presence of acid. Okay, so I'm going to add the ethylene glycol to this ketone. The ethylene glycol is not going to react with the bromide. It's going to react with the carbonyl, and so I'm going to end up forming a five-membered ring. So I'm going to have a CH3 attached to the carbon with the ethylene glycol, in this case ketal, being formed. And then on the other side, I'm going to have my bromide. So that's going to be my protection. Because the critical part here is that ketal is going to stay a ketal until I add acid and water to it. And when I add acid and water to it, it's going to go back to become the ketone. Kyle? Exactly. It's protecting the reaction with the Grignard. So I'm protecting it. Sometimes people will call this masking. Like, in other words, I've taken a ketone and turned it into another functional group that is going to become a ketone when I want it to become a ketone, but it's not going to react as a ketone. So I'm protecting it from reacting. As long as I don't touch it with water or acid. Okay. It'll stay and it'll stay and it won't react. Everybody understand those caveats? So now what I can do is now I can add my magnesium, and because I'm operating under basic conditions, because it's C minus, so I'm operating under basic conditions, that C minus will not react with an acetal or with a ketal. So there's nothing for it to react with. The Grignard stays intact. And now I can go ahead and now I can say, okay, now let's add my CO2 like a normal Grignard, and the C minus will come over, attack the carbon, and then I will end up with the carboxylate. So I've added my CO2 to the end of the chain. Now I haven't added any acid yet. Right? This is still under basic conditions. So now, when I do the final step in the Grignard, which is always H plus H2O, what's going to happen? I'm going to protonate my carboxylate to make the carboxylic acid, and what else is going to happen? The acid, the ketal in this case, is going to be converted back to the ketone. So in this case, I don't have to have two separate steps. The acid that turns the carboxylate into an acid is the same acid that's going to convert the acetal all the way back to the ketone, or the ketal all the way back to the ketone. So then I'm going to end up with my final product. Okay. So that's the idea of protection. I'm protecting the carbonyl, in this case the ketone, or the aldehyde, from reacting with either the reagent I'm going to use or what I'm going to turn the other part of the molecule into, which in this case was the Grignard. By the reverse of the reaction that you just wrote for your take-home quiz today. So I can start it. Maybe that should be the take-home quiz for next week. But then what would you do? You'd write exactly the opposite steps. So if I now add acid to this, what happens? I'm going to protonate one of these oxygens. Right? So I'm going to end up with my oxonium ion. And I'm just going to write that so I don't have to write the entire chain. And now what happens? Now this pair of electrons goes to the oxygen. The first one comes off. What does the water do? It hasn't. It's got to add first. Now the water adds to the carbonyl. What's going to become the carbonyl carbon? It adds to the carbocation. We'll end up with an OH there. Then the acid's going to react with the other oxygen, and the dialcohol comes off. So it's exactly the reverse of what we like I said, what I hope you did for today. And the key to this is that, if I want to go all the way back to the carbonyl, I need to use excess water as the reagent to push the equilibrium all the way back. Brian?
When we are writing the mechanism for protecting, do we have to, I'm trying to word it, like, draw the molecule reaching out on the ring, or do we just say that it is forming a ring?
You have to show the other oxygen by arrow adding to the carbon.
And then can we just skip straight to the ring, or?
Well, you're going to skip to the ring with the H on this side with the plus. You're going to skip to this part. And you're not really skipping anything, you're going to that. And then the H plus gets lost to form the final product. So if you think about this step right here, after the water leaves, you've got a carbocation. The O is going to come in and add to the C plus. So that's the mechanism.
So we can have like it reaching around to come back to it and then just go to the ring.
Yeah.
Okay.
Yeah, once this OH adds that carbocation, you've got the ring. What?
Could you finish drawing?
Okay, there. Right, because that's the reverse step. So if I add the OH to the C plus, that's what I'm going to get. I know what you're saying. You're saying if you had the plus, it depends on how you draw the molecule, right? If you draw your O, then down here you've got your OH, and then over here you have like your H or whatever, in your R group there, then you have to say, well, I got to this has to reach around and do that. That's fine. It's not really reaching around though in the tetrahedron. If you write it like I wrote it, then it doesn't seem like it's far of a stretch. And in reality, it's not much of a stretch. Sarah?
So this is
I started the reverse reaction of basically what I asked you to do for the take home. So if you take the mechanism, if your mechanism that you're going to hand in is correct, then if you wrote the steps backwards, you would get how to deprotect the ketone. It would be the same steps, only in reverse order. And we're going to find that with a lot of these reactions. Any reaction that's in equilibrium like that, the reverse is the opposite of the forward. So same mechanism, just reversing the steps. Reem?
Say you just ask us to list the reagents we would need to go from one step to another. Do you always want us to protect or only when specified?
Probably only when specified. I'll have to tell you when to protect. Just like I'll have to tell you when to block. Right? But there's two important reacting the ketone with the ethylene glycol. There's two reasons for that. Number one is protection. But number two, making the cyclic acetal or ketal is the normal way we push the equilibrium towards the acetal or the ketal. The other ways to do it are to make the ketone and aldehyde really unstable. Those aren't realistic. I mean, it explains why if you go grab a bottle of formaldehyde, I don't think they use it in biology to preserve dead things anymore. I think they just use methanol. But if you had to go get a bottle of formaldehyde, number one, formaldehyde's a gas. So you would open it up and there'd be nothing except gas. But when it's a liquid, it's that hydrate in water. That's not a normal situation. This is the normal situation. Making the cyclic acetal or ketal, because that can be isolated and I can make a crystal out of it, or it's a liquid, I can purify it. I mean, I can do tremendous things with this. I can column chromatography it as long as it doesn't touch acid. Bless you. The minute it touch acid, it's back to the ketone. So that's why this is the way we usually make acetals and ketals. When we want to, this is what we make. Is everybody kind of okay with? Because there's two aspects to this. First is the mechanism that I ask you to do for the quiz. And that's just making an acetal or a ketal, only making a cyclic one. The other part is using this to keep the ketone from reacting with something else. What else did we have? We had Bayer vinegar, right? So the Bayer vinegar reagent is first of all, the reaction itself is an oxidation, which should tell me that I'm doing what to the molecule. If I said I'm going to oxidize that molecule, what am I doing to that molecule? Inorganic, not general. I'm oxidizing it. Adding oxygen or removing hydrogen, which does correspond to losing electrons. So if I'm going to oxidize something, I'm going to add oxygen or remove hydrogens from it. So this is an oxidizing reagent. And if you go back and you take a look, where have we used the peroxy acid in the past? Making epoxides. And there, what were we doing? We were oxidizing, we just weren't saying it. Right? We were saying, take your peroxy acid, react it with an alkene, and you will make the epoxide. But it's oxidation. So now what I want to do is I want to take this peroxy acid and I would like to react it with an ester. Okay, so we've got like R1 and R2. And so what Bayer and Villiger found out was that if you took a peroxy acid and you reacted it with the ester, sorry, not an ester, a ketone. Yeah, ketone. If you reacted it with a ketone, you make the ester. So the peroxy acid then will add an oxygen in between the carbonyl and one of the alkyl groups. Okay. By a mechanism that we're not going to learn. But you can kind of think of it as taking an oxygen and plopping it into the bond. Sort of like what it does with an alkene. Well, which alkyl group? In general, the larger alkyl group. So what I'm going to end up doing then is adding the oxygen in between, let's say, if R2 was the larger group, the peroxy acid plus that ketone would make that ester. So I'm going to put the oxygen right in between the carbonyl and the larger alkyl group and make the ester. So this is a way to turn a ketone into an ester in one shot. And what would be the advantages of doing that? Well, it's one step. And I know to make an ester, right, because we went back to the esters experiment this week in lab, that in order to make an ester, I've got several options, one of which is Fischer esterification, where I take a and carboxylic acid, react an alcohol with the carboxylic acid with an acid catalyst, Fischer esterification, make the ester. Problem, equilibrium. Get around the problem, what do we use? Acid. What did you say? That's for Fischer. I want to do something different than Fischer. But it's not that much different. Use an acid. Chloride. How about an acid chloride? How about a carboxylic acid chloride? What's today? Oh, today's only Wednesday. So it would have been last week that we went over this. So acid chloride plus alcohol makes ester. Better, no equilibrium still. I got to make the acid chloride, which we never went over, which I haven't reviewed. I know. I know. What reagent do you think I'd use for that? Your hint is it's something that turns an OH into a Cl.
Oh,
PCl3. PCl5. SOCl2. Those are great reagents to make the acid chloride. But see, to beat the equilibrium, I had to add in another step. So my point here, because I probably got the point got lost at some point, even to me. What was my point? I want to make the ester, and this way I can make the ester from the ketone in one shot. Now where it becomes really important, and I probably said this in the video, was let's say I have a 5-membered ring. That's not 5-membered. Let's say I have a 5-membered ring ketone, and I want to make the cyclic ester out of it. Or I just in general want to make the cyclic ester. You might say, well, okay, I'll use my Fischer esterification that you just reminded me of. I think I need one. Yep, I need one more carbon in there. So you could say, oh, well, I'll do this. I'll take this molecule, and it'll react intramolecularly. And this OH will end up coming over here and adding to the carboxylic acid so that I'll make that 5-membered, or actually in this case I'm going to make a 6-membered ring. So if I wanted to make, let's say, this molecule a cyclic, if I wanted to make a cyclic ester, which is called a lactone, well, you would have to slow it down from the 2 or 2.5 speed you were watching it at in order to get me to say lactone. Maybe you can petition them. I don't know how people can handle 2, but I've said that before. I've tried. So lactone. So we can make the lactone by this intramolecular reaction, except in real life, I got a problem. And real life is anything but paper. On paper, this works great. If I go to the lab, I'm going to have a problem. And my problem is, again, this isn't just one molecule. This is lots of molecules. So this OH might decide to react with a carboxylic acid of another molecule. And I might end up making a long chain of those esters, which may not be a bad thing because that's called a polyester, right? That probably brings up the cheesy, 70s leisure suits that were made of polyester. But that's how you make polyesters, and we'll talk about that later, because that's actually used in fabrics and it's used in other plastic materials. But if I want to close the ring, I'm going to have a little bit of trouble with that. So my point is that if I started with the 5-membered cyclopentanone and said, let me just go ahead and add the Baeyer-Villiger reagent to it, I'm going to make the 6-membered ring ester in one step. And so all I have to do is start with the cyclic ketone. And the cyclic ketones would be relatively easy to make. Start with cyclopentane, put a bromine on, but from free radical halogenation, change it over to an OH with hydroxide, and oxidize it to the ketone. Easy steps. So this is the real importance of Baeyer-Villiger, is to be able to make lactone rings. Because otherwise you're fighting the molecules creating chains or creating rings. And it's tough to control that. Sarah?
I'm confused about the equilibrium with the acid. What is that?
Remember, there is no equilibrium for an acid chloride.
Right.
So probably the quote-unquote best way to make an ester would be to react the acid chloride with the alcohol, because it would go 1-to-1 mole ratio. I don't need any excess because I'm not fighting Le Chatelier. But if I'm doing Fischer, I have to fight Le Chatelier and use excess reagents. What else? If I said, I want you to make that molecule, Rito Krauss. Okay. So now that we know all the aromatic chemistry, we have to be careful because there's no circle in that cyclohexane ring. Right? No, you're not the first and you will not be the last person to do that. I can guarantee that. So you have to be careful when you're looking at cyclohexanes and aromatic rings. They are different. Yeah, so no Friedel-Crafts. And also, well, now the other reactions that we learned the other day might be good. Like Heck coupling or, well, Heck coupling, no. But Suzuki might be okay.
Do you have like a vault of just practice problems? I know that you got rid of like one of the software do, I think, in the past with the whole bunch
Oh,
of
the
bugs.
sapling?
Yeah.
Yeah, everybody's happy
Because
about that.
I could go and get a mock exam, but that's
Well-
like all of that. So I would like to know what.
Well,
I would
if
like to be
you,
able to do now.
so I'm gonna put some practice problems in today's folders. I'm gonna put them in today. Before I leave, I'll put them in. But my suggestion is if you want more practice problems is, I would say that the last 5 years of exams fit the timing when I flipped the class. But before the last 5 years of exams, the exams probably 3 and 4 would have tons of problems, but they're not, you can't really use those as practice exams because they also have stuff from before on them. So if you go to the older exams, and there's got to be stuff back to 2005 and 4 and 1. I think that's when I switched from a Mac, so I don't have those files anymore. But there's 15 years of problems there. So if you want to use practice problems, use the real old ones, and then use the newer exams as kind of a practice exam. So if you cut the answers out, and then you can go ahead and do that. But I'll put some more on. I'll put some more practice problems, and the answer keys for all this stuff I will link up after class. So what was I doing? Oh, this. So we want to make this. If I said, make this from like cyclohexane, a lot of ways we could do that, right? And we could think about using Suzuki coupling. But another way to do it is the Wittig. And in German, W is a V. So it's Wittig. So the Wittig reaction allows us to basically say, okay, I'm going to bring these two parts of the molecules together and form a double bond. What parts do I need? I need the ketone or the aldehyde in this case. And then I need the phosphonium or whatever, the phosphonium ion. The ylid is what's formed in between. So I would need to react my alkyl halide with the triphenylphosphine, deprotonated with butyl lithium to make that intermediate. So I can put this molecule together by using a Wittig, or a Suzuki, or lots of other methods, including even thinking about a Grignard. So when you look at like the Wittig, okay, it's another reaction, yes. But the real power of this is that no matter how complicated my left and right hand structures are, I put the right groups on, I can couple them together to get my final molecule. And that's kind of what we've been doing for the last week and a half or so, is seeing some of those reactions, because that's what real synthetic chemists do. This group works on this part of the molecule, they work on that part, and they bring their parts together, which are really complicated, and they stick them together through Suzuki or Heck or Gilman or Wittig. Okay. All right.
How can you make this from a benzene ring though? Like, how do you make it?
Well, it doesn't have a benzene ring.
Yeah, I thought you said that.
No, you can't. You couldn't do it. You can't. You couldn't do a.
You cannot make a benzene.
You couldn't.
ring
You,
to-
yeah, you couldn't. You couldn't make a ben. You couldn't have the benzene ring be attached through a double bond. That's 5 bonds. Okay.
Make that. Oh well, I guess like H2 of palladium. Like, could you make a benzene into a?
That's really tough. All right, I'll take your homework. Your homework problems there. I'll have everything ready after break. Oh, you have a suit. You must have. Hey, Jen. You have a suit. You must have interviewed today.
I have an interview today. With Dr.
That's how I knew, because you had a suit on.
Oh, yeah.
Have a good break. Probably very little of that. There's enough reactions. That's what we're also going to do. So there'll be a question as the last exam, which was so. Okay. No, I have to. I'm. Yeah, you'll have to come later. Come after 3, because I've got to go to Dr. Watlin's class.
Oh, you do? Okay.
Why? We're doing a case study on ethics, so that's where I have to go now.
Okay.
I'll be in there after 3.
Were you able to go from my schedule yet?
I think it's okay.
Okay.
I haven't released you yet, but we have time to do that.
Okay.
Yeah, that seems reasonable.
Okay.
Okay. Do you want to take your well, no, if you want it, you can go up and take it and then just give it back and give it more stuff you want to. I can do that.
Do you think there will be an issue with either having to take the Orgo lab final or Chem lab final early?
Yes, there will be, because they're scheduled at the same time.
So I
But
can't
since you have,
I can't take one of them before.
yeah, you can take one.
Okay.
The only problem, we'll let you take we'll let you take face at the normal time.
Yep, you too.
So I filled out the form to take biochem lab.
Yeah.
But I know that it asks for either like graduation. And so I'm like kind of on a boat with like 3 years versus 4 years, and it's not set. But I wanted to let you know that like if there's a possibility, I selected like 2020, but like there's a possibility that I need to finish in 3 years. So.
Okay,
But
so so you need to take it either in the fall or the spring.
Yeah. So like should I?
Send me an email. Send me an email, because I'm doing that tomorrow.
Okay.
Send me an email and just say that you need to take it like either fall or spring
Okay.
of
Alright.
next year.
Okay.
Because my whole issue with the whole forms is that I need to be able to tell. I need to be able to know that when people